Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is KP and simultaneous reactions, and the sections in the textbook are 16.3 to 16.4. So here are the two learning outcomes. At the end of this, you'll know and understand several qualitative aspects of what the value of KP means, the quantitative value, and you'll be able to determine the equilibrium composition of multiple simultaneous reactions. So first I just kind of want to go through some general aspects of KP. And so first of all, I want to remind you that KP is simply a function of pressure. Remember, I can determine KP by taking the exponential of minus delta G star over RT. Okay? And when I wanted to determine G, well, I had all the stoichiometric coefficients times each individual G star, the little g, and that right there is just simply H minus Ts, where that's the standard state entropy. This is the standard state Gibbs energy. And for ideal gases, we've got H, which is just a function of temperature. And so what we realize is that this whole function here is only a function of temperature. That's only a function of temperature. Therefore, this whole right-hand side is only a function of temperature. In Kp, the equilibrium coefficient, therefore, can only be a function of temperature. Let me talk something about reverse reactions. So let's just have a simple reaction, A going to B. And so if I wanted to know what Kp of that reaction right there, Kp is, well, it's going to be the partial pressure of the reactants, which is Pb, over the partial pressure of the partial pressure of the products over the partial pressure of the reactants. So Pb over Pa. Now, if I was to look at the reverse reaction, which is B going to A, what I would then have, I'd have a Kp value that's going to be somewhat different. Now it's going to be the partial pressure of A over B. Okay, so what I've written, when I reverse the reaction, I realize that this value of Kp is just the inverse. And so if you reverse the reaction, you want to take the reciprocal or the inverse of your Kp value. So the direction of the reaction of how it's written matters. Let me remind you a little bit about reaction completion. And sort of as we just saw this reaction over here on the left, A going to B, what I realize is that if this reaction goes nearly to completion, I have lots of B, the partial pressure of B would be larger. So therefore, the more it goes to completion, the larger the value of Kp. So large values of Kp indicate reaction going to completion. So for combustion, we saw Kp values can be in the order of 10 to the 20 or 10 to the 40. They can be really, really large values because essentially combustion reactions go almost entirely to completion. Let me mention something about the total pressure. And here's about the total pressure in the system. And it turns out that the total pressure in the system doesn't matter. Now, one, I can realize that just because, remember I said Kp is only a function of temperature, so you know it from there. But where it gets a little confusing, if you come back to a form of Kp that we had where we had the number of moles of product to the stoichiometric coefficient, we had the number of moles of reactants to their stoichiometric coefficient. Sorry, those are big pi, those are being multiplied by each other. And then we had the total pressure over the total number of moles. This is total pressure to delta nu. It looks like Kp is a function of pressure. But we saw in the previous video that if I change this value, these values right here end up changing and adjusting such that Kp is going to be equal to a constant, or Kp remains only a function of temperature. So it looks like it's a function of pressure, but it's not actually. Let's look at some more aspects of it. First, let's kind of mention something about inert gases, and we saw this in the previous video. And then inert gases don't affect Kp at all. In fact, we know it because when you wanted to determine the equilibrium condition, right, we just had G times nu is equal to 0. That was our equilibrium condition. And this G right over here, we're summing over all the reactants and all the products. Reactants and products changing in sign by nu. So inert gases don't appear in there at all, so therefore they're not going to affect Kp. What we saw is that because of that form from the previous slide, if I come back here really quickly, the previous slide where I have the N total down here, that affects, inert gases affect this number, and so what you end up doing is affecting the composition, again, just like changing the pressure affects the composition, but it doesn't affect the value of Kp. Let me mention something about the coefficient values. So let's write a reaction A going to 2B, for example. And if I write the Kp for that, I've got my partial pressure of my reactants to PB, and then I'm going to square it because it goes to the stoichiometric coefficient over P sub A. Now, if I was to write this reaction in this form instead, if I have 1/2 A going to B, right, it looks kind of the same. I just multiply through by 1/2 on that. But now if I look at my Kp value, I'm going to have a different one. I'm going to have the partial pressure of B over the partial pressure of A to the 1/2. And this right over here is Kp to the 1/2. So effectively, if I'm multiplying through by 2, I'm effectively squaring. And if I multiplied through by 3, I would be cubing when I'm going it. So those values of Kp change. So you want to make sure that your stoichiometric coefficients correspond to the correct value of Kp you're looking at. Something interesting about ionized gases, which can happen at really, really high temperatures. And ionized gases, for example, say I started off with H2, and then it became dissociated and turned into 2 H's, and then those became into maybe 2 H pluses plus 2 free electrons, and that can happen. And that's really high temperatures. Effectively, you're stripping off the electrons. These end up forming a part of the cloud, so you have some electrons in there, and then your H pluses. And so they end up appearing in your Kp equation as a product. And so you would end up having the partial pressure of H plus, as I have it there, would be squared. And then you would have the partial pressure, more or less, of the electron cloud squared all over P sub H. And that would be squared as well, since I got 2 as I've written that equation there. And then one of the last things I want to mention is none of this says anything about kinetics at all. These are all equilibrium compositions. It says nothing about the rate at which it's occurring. So kinetics and equilibrium are completely decoupled. All right, so let's look at what happens when we have multiple reactions. And so we're going to do an example here in a minute. And so let me just kind of set the stage of what I mean. Imagine I take atmospheric air, which is a mixture of oxygen and nitrogen, and then I was to heat it up to a really, really high temperature. What would I end up forming? What would I have? Well, what I could do is I could rip apart the O2s, so I could have just oxygen. I could rip apart the nitrogens, I could have just N. And then what might also happen is that they could get ripped apart, and then I could form NO, and so I could end up having those 3 components right there. And so if I look at it now, I've got this O2 plus N2 going to these 3 things right here. And so these reactions, you realize, can start to get somewhat complicated. And what you want to do is break this down into manageable parts. And so for now, I'm going to go ahead and neglect this dissociation of nitrogen, and I'll return to that at the end of the video here. But for right now, just believe me that actually doesn't tend to happen. So we'll just look at the formation of O and the formation of NO. Well, I could take 2 reactions. I could take O2 going to 2 oxygen. There's one part. And then I could also look at O2 plus N2 going to 2 NO. And those 2 equations right there are going to add up to the equation that I have up here on the top, where I'm forming some O's and some NO's. Now, each of those are going to have a Kp value. I'll call it Kp1 and Kp2. And so I can go ahead and solve the equilibrium conditions, both of these equilibrium conditions at the same time, and get my net reaction. And so let me just kind of mention, all I need to do is get a set of equations that add up to the net equation. What set of equations I use doesn't really matter. So, for example, I'll just do an arithmetic example. Imagine I have the equation 3x plus 2y is equal to 5. Now, I could go ahead and arrive at that equation by writing 2 simple equations. I could just say, for example, 3x is equal to 2, and 2y is equal to 3. And if I add these 2 equations, I get 3x plus 2y on the left, and 2 plus 3 is 5. And so I would end up having, effectively, this summed equation. Now, if I look at what my values of x and y are, I realize x over here is equal to 2/3, and if x is equal to 2/3, I end up putting 2/3 into there, and I can realize that y is going to be 3/2, right? So those are my values of x and y. Now, however, I could have arrived this another way. I could have had 3x plus 2y is equal to 5 again. And I could have written a different set of equations. I could have said x is equal to 2, and now my other equation is going to have to be 2x plus 2y is equal to 3. Now, if I add those 2 together, again, I get this equation down here. But clearly now I said x is equal to 2, and over here I said I had a different value of x, and so I'm going to end up with a different value of y just as well. I'm going to add y at, I think, minus 1/2. So my point that I'm making is that here's my net reaction, and I don't care how I get to my net reaction. I can get there with any sets of equations that end up with my net reaction. So what I've done here, I could go back to our chemical equation, O2s and N2s, and I wanted to form some elemental oxygen and NO. I found two equations that I know Kp values for that I can go ahead and sum up and get this one. So there's not only one route to getting to the answer. All right, so now let's actually go through and do numerically the problem that I was just looking at. So I have atmospheric air, and then I'm going to go ahead and take that to 3,000 Kelvin and 2 atmospheres of pressure. Let's find out what our equilibrium composition is. And so again, I'm gonna neglect the dissociation of N2, and so we're going to look at these two reactions. We're going to look at O2 going to 2 oxygens, and if I look up that Kp value, the natural log of Kp in table A28 is minus 4.357. And then the other reaction we look at is 1/2 N2 plus 1/2 O2 going to NO, because that is also in the table there. And the ln of that Kp value is minus 2.114. And again, those are out of table A28. Okay. So now let's go back to our problem. Our problem says we take atmospheric air, which would be O2 and 3.76 N2. That's our 21 to 79% mixture. And I think of that, we had that at time 1. Now we're over here at time 2. And what we're going to end up with is, well, we're going to have some oxygen left over, I would assume, and some nitrogen still. But then what I did is I formed some O and I formed some NO. So let's put our coefficients in front of that. I'll just use X. I'll call it X of O2, X of N2, X of O, and X of NO. So I have those 4 unknowns. And that's going to go ahead and tell me what my equilibrium composition is. It's going to be all those different values of X. Now I have 2 elements in here. I have oxygen and nitrogen, so I can do balances for both of those. So let's do our oxygen balance. On the left-hand side, I have 2 oxygens, 2 O's. So I know 2, and that's going to be equal to, when I look over things on the right, I have 2 times X of O2, right? And I've got X of O and X of NO. That's where oxygen appears. 2 because it's an O2, and then just 1 because it's an elemental oxygen, and only 1 oxygen in the NO. And now let's do our nitrogen balance that we have, and that's going to be 7.52. That's 3.76 times 2. I'm looking at single ends here, and that's going to give me X of NO plus 2 times X of N2. So let's kind of recap where we had 4 unknowns. Now I have 2 equations, so I need to write 2 more equations. So I have 4 equations and 4 unknowns, and those are going to come from my 2 Kp equations. So I'm going to write down my equilibrium of that. So I'm going to start off with this oxygen, and if I look at I'm going to take the exponential of minus 4.357. That's going to give me 0.0128. This is the oxygen equation. So I've got to look at this equation as I have it written. I've got my products. The products is X of O squared, that's the stoichiometric coefficient, over X of O2. And then my total pressure is 2, and that's all over N total. And then that's going to be equal to the power of 2 minus 1. So we're all going to go to the 1 power. And now my second equation is, I'm going to take the exponential of minus 2.114, 0.1208. And now that's going to be equal to, now we're going to go ahead and look at my products. My products, I've got NO as a product, X of NO, and then my reactants are O2s and N2s. So I have X of O2 and X of N2. And both of those to the 1/2, or the square root of that whole thing. And then 2 atmospheres of pressure over N total. And now I've got my stoichiometric coefficient is going to be 1 minus 1/2 minus 1/2. 1 minus 1/2 minus 1/2. That's equal to 0, which means that whole thing is going to be equal to 1. And so I can go ahead and just look at my X equation. So here again, I got 4 equations, right? I'll go ahead and, there's equation 1. There's equation 2, here's equation 3, there's equation 4. I need N total, so that's actually kind of maybe a 5th equation. So the total number of moles is just going to end up being X of O2, X of N2, X of O, and X of NO. Maybe you can do that as my fifth equation. So I'm going to go ahead and solve those 5. And this is most easily done in the ES when you're doing these simultaneously. Let me move over there. Okay. So here I have it in EES, and so here are my 5 equations, and that's all that I've got. I've got my oxygen balance, as I have written, and then my nitrogen balance. Those are the first 2 equations I wrote. And there's my equilibrium equation, my Kp equation for O2, and my Kp equation for N2. And you'll realize that N2, I realized that last term, the exponential was 0, so that term was 1, so I didn't even put that on there. And there is my total number of moles. So 5 equations, 5 unknowns, so let's go ahead and try to solve that. Okay. And it gave me an error that it's trying to raise numbers to a negative power. Well, that's because those values of x, we know those can't be negative. We can't have a negative number of moles. So what we're going to do is we're going to go up under Options and Variable Information, and we're not going to let any of those be negative. So we'll go ahead and set those equal to 0, because we know that that's the smallest it could be. Can't have anything less than nothing, right? Okay. So let's see if that fixes the problem. And it looks like it did. So there's my solution. I've got my equilibrium composition of N2s, NOs, Os, and O2s. A little bit of sanity check. I would expect that N2 can't be any more than I started with my 3.6. So that's clearly less than 7. That number went down. My oxygen is less than 1, so that one went down. So that makes some sense that it got consumed. So it's good to kind of do a little bit of a sanity check. Okay. Now, one of the things I mentioned was that I didn't bother with the dissociation of the N2, and so why was that? Why did I make that assumption? So we can actually kind of know why I did that. Is if I come over here, here's table 828, and let's look at the dissociation of nitrogen equation. That's this fourth column right over here, and we were at 3,000. So if at 3,000 degrees, my value is minus 22, and that's the natural log. So if I take the exponential of minus 22.357, that's a teeny number. It's like 10 to the minus 20 or something. Remember, large values of Kp go to completion, so small values mean it doesn't happen. So relatively, this equation of N2 to 2N doesn't occur at all. Now, you could have gone back to the problem that we just solved and have added a third equation to it. And you would have had a third Kp equation that would have appeared in here that we would have done. And you could have went ahead and solved that equation again as well. And what you would have found is that you would have had effectively none. So what we would have done is we would have adding x of n. So there's my extra unknown, and there's my extra equation. And so I still have, now I have 6 equations and 6 unknowns. And when we solved it, we just find out that x of n was effectively equal to 0. And in fact, if you want to stick that in there on your own and find out what its effect is, it might be a good practice. And you should find out that number is going to be incredibly small, if not effectively just 0.